Hi, welcome to Lesson 2 of Module 4. The title is Linear and Nonlinear Expressions in X. Okay, in the last lesson, in Lesson 1, we practiced using symbolic language to represent mathematical concepts or ideas or problems. And we're going to continue along those lines today, and we're going to talk about what it would mean for an expression to be linear or nonlinear. Okay. So before we get started with examples and exercises, I just want to go over some vocabulary. A lot of this vocabulary has been introduced in 7th and 6th grade math. So I just want to make sure we're all on the same page. And so anyway, here we go. So a term in mathematical, in this context, is either a single number or a variable, or numbers and variables multiplied together. So a term could be something as simple as, I'm going the wrong way. A term could be something as simple as just a number, the number 3, say, or it could be a variable. It could be like a variable x, or we call it y, or whatever. Or it could be a combination of numbers and variables. That could be a term. I'm putting commas in between my terms. We could have something like a number and a variable to a power. That would be a term. What wouldn't be a term is this, numbers and variables added together. That would not be a term. Okay, so only multiplication for terms. So those would all be examples of terms. Okay, so a coefficient is the numerical multiplier of a variable. So in the term that we wrote up above, 3x, the coefficient is 3. Okay, the variable is x, the coefficient is 3. Co just meaning with. So it's just the number that goes with a variable sometimes. Okay, an expression is one or more terms added together. So I could have 3 plus x would be an expression, the sum of 3 and x. Okay, so we could write it as 3 plus x. An expression could also be any of these single terms that we have up here would all also be expressions. So each of those would be an expression, but expressions can include more than one term. So we can add those together. I could have something like x squared minus 3. That would be an expression. I could have, well, you get the idea. I could have several terms together. I could have 2 plus 3x plus 1 over x. Okay, so could be lots of different things like that. Okay, so expressions, those are expressions. Now there's something missing in an expression, and that is an equal sign. But an equation is just when we set two expressions equal to one another. So there's an expression. I'm saying 3x equals x squared minus 3. So there's an expression on either side of an equal sign. So what I'm saying is that those expressions are equal. So if I was going to solve that equation, I'd have to find a value for x that would make both sides of that equation the same. Okay, so there's some terminology there. By the way, I'm emailing you these PowerPoints too, so if you do want to print them out to make your note taking easier, you could do that. Okay, so we just talked about what an expression was. Do that every time. We just talked about what an expression was, and it's a term or a collection of terms added together, sums of terms. Linear expressions have very specific rules, and the reason we want to be able to differentiate between linear and nonlinear is because it helps us to, when we go to graphing these types of equations, if we know that they're linear, we know what to expect about the shape of a graph. And, you know, if we know that a graph is not going to be linear, then we might know that we need to plot more points or think about it a different way. So we're going to learn to just recognize when an expression is linear, okay? So there's just a couple rules that will let us know that. So expressions are sums of constants. Now that is I didn't put that on our list of vocabulary, but a constant is just a number, doesn't change. That's as, you know, in contrast to a variable, which does change, which can change depending on what value we assign to it. So constants are just numbers. Okay, so linear expressions will be sums of constants and products of constants and x raised to the power of 0 or 1. Okay, so we're calling these linear expressions in x, but just know that it could be any variable. You don't have to use x, but basically what we're saying here is that they're one variable. So these are linear expressions in one variable. Okay, so they're going to be constants. So I could have just a constant, and then a product of a constant and a variable, and it's a sum, right? So I'd have 3 plus 2x, that would be a very simple one, raised to the power of 0 or 1. So x to the first power is just x. So we don't usually write it, but it's there. So that would be a linear expression. If I had 3 plus 2 times x to the 0 power, it would also be a linear expression. But remember that x to the 0 power is going to equal 1. So it's not gonna vary, but it's still going to fit the definition of a linear expression in x. So we could have just something simple. It could just be 2x alone could be a linear expression. Notice again, I'm not putting any equal signs here because we're talking about expressions right now. We're just talking about expressions. They don't have equal signs. They're just kind of, you could think of them as mathematical phrases or kind of incomplete sentences. Okay, so those are linear expressions. And sometimes it's easier to recognize a linear expression if you know what a nonlinear one could include. And then you can see that. So nonlinear expressions in x can include any element of a linear expression, but will also include a term with x raised to a power other than 0 or 1. So, you know, I could go off that. We could have 3 plus 2x plus x squared. Now that's going to be nonlinear because it includes this term that has a power other than 0 or 1 on the variable, okay? I can put a power on a constant, it doesn't matter. That would still be linear. Okay, let's think of another one. What would be another power other than 1? What about 1 over x? what's the power on x there? Well, if you remember from our first module, the rules of exponents, if I have x in the denominator like that, this is equal to x to the negative 1. So 1 over x would be nonlinear. And I could have 1 over x plus 3 or whatever. That's going to be nonlinear because it includes that term that has an exponent other than 0 or 1. Okay, so we've got this x squared here. We've got 1 over x. Anything, x cubed minus 2, whatever. You might think that that's not a sum, because remember these expressions are sums. But remember, anything with subtraction I could represent with addition. That'd be the same thing as x cubed plus a negative 2. So this would still be a sum of various terms. Okay, so we're going to, if that's not clear to you right now, don't worry, because we're going to do lots of examples here. Okay. Okay, so let's just let's try to classify some linear and nonlinear expressions. So I'm going to write them up here, and then I want you to think about which column it would go in. Okay, so 5x plus 3. Okay, and that would go in the linear expressions column. Okay, so we'll put that there. It's a sum of terms. There's 2 terms here. Not very well written, but it's an x. There are 2 terms, 5x and 3, so it's a sum. 3 is a constant. X is to the first power, so that qualifies it as a linear expression. Okay, let's do another one. 9 minus x squared. Okay, so which column would that go in? Well, it has a variable term. Whoops. It has a variable term that is raised to a power other than 1, and so it's a nonlinear expression. And I'm trying to cut and copy it. No, it's not going to work. One more time. Here we go. There we go. Okay, so 9 minus x squared would be nonlinear. Okay, let's do another one. Let's see. X over 2 plus 3. Where would that go? Okay, because x is in the numerator, the power on x is the first power. So it qualifies for a linear expression. And so let's see if I can get it to go right over here. There we go. Okay, so x over 2 plus 3 is linear. How about this one? 11 times x plus 2. Linear or nonlinear? Okay, it is linear. Okay, got it. So it goes down here. Move it over maybe. There we go. So that is linear. Why? Because the power on the variable is 1. And we could rewrite this as 11x plus 22, right? So then you can see it more clearly that it is, it's a linear form. Okay. Let's do one more. So what about 7 plus x to the negative 4 plus 3x? Okay, linear or nonlinear? Okay, well, it does have a term with x to the first power, but it includes a term with x to a power other than 0 or 1, so it is going to need to go in the nonlinear column there. Okay, so let's move on and do talk about a few more things here. All right, let's talk about this expression in x right here. Let's start off by saying, is it linear or not linear? So hopefully you'll notice that because it has the power, that the variable is raised to the 5th power. So this is not going to be a linear expression. This is going to be nonlinear. Okay, so this expression has, get a different color here. This expression has 2 terms, and they are 4. The first term is 4. The second term is 3x to the 5th. Okay, so terms, remember, in an algebraic expression like this, are things being added together. Okay, so there are 2 terms. 4 is a constant term. So I'll just label it like so. 4 is a constant term. And 3x to the 5th is a variable term. And this term here, right here, this term 3x to the 5th has a coefficient of 3. So the coefficient of that term is 3. And as we already said, it's nonlinear because of the exponent on the variable. Okay, remember, you could have an exponent on a constant, that wouldn't make something nonlinear, but the exponent other than 0 or 1 on the variable will make it nonlinear. Okay, let's talk about another one. Okay, so let's look at this expression. Got 7x plus 9 plus 6 plus 3x. Okay, so how many terms would this expression have? Well, this expression would have, the way it's written, it would have 4 terms, and they would be 7x, 9, 6, and 3x. So remember, we're looking for these addition signs, okay? Because terms are things being added together. So there are 4 terms in this expression, but this expression could be simplified or transformed by putting some things together. So one real easy thing would be to put the x terms together. I can move things around using the commutative property because everything here is being added. So I have plus 9 plus 6. Okay, so we could see that we could group the 9 and the 6 together and get 15. And we can group the 7x and the 3x together, and we can think of this as 7 plus 3 times x. So I can, using the distributive property, I can factor out the x, and I'm left with 7 plus 3 times x. So this would be, and these are added together. So this expression could also be written 10x plus 15. So this expression and the original one are the same, just rewritten a little bit differently. Okay, and our new expression down here, 10x plus 15, the x term has a coefficient of 10. There are only two terms in our new expression. The first one 10x, the second one 15. This is a linear expression because the power on the variable is a 1 right here. We don't have to write it, remember, but it's a 1. And this, we could have noticed this one, our original expression, was also linear because the variables are raised to power of 1, and otherwise there's only constants. So, okay, so I'm going to ask you to think now, looking at this expression, how many terms does this expression have? So think back on our definition of terms and think about that. Okay, I wish you were there, because hopefully you're saying that this has 3 terms. The terms would be 5, 9x times 7, and 2x to the 9th. Okay, so the reason that 9x and 7 aren't separate terms is because they're being multiplied. 9x, it's 9x times 7, not plus. So it's just one term there. That term could be rewritten as 63x by multiplying the 9 and the 7 together, because this would just be 9 times x times 7 times x times 7. Because remember, when we write the coefficient out in front of the variable, it means multiplication. It means I'm multiplying by that number. Okay? Okay, so here's another question looking at this expression. What are the coefficients of the terms here? Okay, so there are 2 terms with coefficients, and the coefficients are 63 and 2. The term 2x to the 9th has a coefficient of 2, and the term 9x times 7 has a coefficient of 63, because the coefficient is always the number that goes with the variable that's being multiplied by the variable. And last question on this one. Is my original expression up here, is that a linear or nonlinear expression in x? All right. So it's nonlinear, right? Because of this exponent right here. For linear expression, the variables will only have an exponent of 0 or 1. Anything higher or lower, any negative exponents even, makes it a nonlinear expression. Okay, here's another expression. And does this qualify as either linear or nonlinear? Think about it. Okay, so someone might say, but it's not a sum because I have this minus sign here. I have a minus sign, and you said that an expression is a sum of terms. Okay, Well, when we have a subtraction sign like that, what we're going to want to do is to rewrite it with addition. Okay, so if I were evaluating this expression, I would do it from left to right. And when I got to this, I would say, okay, now I'm going to subtract 2. But the subtracting 2 is the same thing as adding a -2. Okay, so this becomes a sum of 1, 2, 3, 4 terms. I have a term with to the power of 1. This is x to the first power. But I have included a term of x to the -6th power. So this whole expression now, because of that term right here, becomes nonlinear. All right, last example before we start our exercises in your notes. Is this linear or nonlinear? Or neither, I guess. Look at it. Think of the definition. Okay, this expression right here has 3 terms. 1, 2, 3. This last term would be, I'm going to do that, would be -4, because I could think of this as plus a -4. So it's got 3 terms, and I need to check the power on the variables. This one has the 1 stated. This one is actually also a power of 1. So I only have, my variables are only raised to a power of 1. And so this is a linear expression. Okay, so now find your classwork, and there are a number of exercises for you to work through. And I'd like you to try these first on your own, and then check them against the video. So we'll go over the directions together, and then I'd like you to pause the video and do that. You can check them one by one, do one problem at a time, or if you're feeling confident, go ahead and do all of them and then come back and check your work against the video. Okay, so let's read the directions. It says, write each of the following statements in exercises 1 through 12 as a mathematical expression. So we're going to use that symbolic language. State whether or not the expression is linear or nonlinear. If it is nonlinear, then explain why. Okay, so looking at number 1, we have the sum of a number and 4 times the number. So remember, we are looking for clue words on these, and this one has some clue words. So I see sum, so there's going to be addition going on. I see 4 times, so it's probably multiplication, and this number is mentioned, so there's my variable. So we're looking for those clue words, but remember, you need to define your variable. You can't just use it, but define it and then write the expression. Okay, so go ahead and pause the video and come back and check as you need to. Okay, so for this first one, this phrase here talks about a number. So we're going to let x be the number that's being talked about here. Okay, so once I know that x is the number, then I can translate this phrase. So I have the sum, so that's my addition right there. The sum of a number, my number is x. 4 times the number would be 4x. And so the sum of a number and 4 times the number is x plus 4x. And that would be a linear expression because the power on the variable is 1. and I can have a 0 or a 1 to have it still be linear. Okay, so if you need to, pause and work on 2, otherwise keep listening. Okay, so for number 2, it's simply the product of 5 and a number. So we'll let x be the number. The translation of that would just be 5x, and it is a linear expression because the power on the variable is 1. Okay, this next one we'll work through. I want to show you my thought process on this. Okay, so for number 3 it says multiply 6 and the reciprocal of the quotient of a number and 7. So obviously we have a variable here, or an unknown, so we're going to let x be the number. Okay, so I'm going to multiply 6 times something, so that's pretty straightforward. It's going to be 6 times something, and that something is the reciprocal of the quotient of a number and 7. So I'm going to start by writing the quotient of a number and 7. So quotient is division, so I could write it as x, because that's my number, divided by 7. But in algebra we really don't use the division sign, so what we want to do is we want to always represent division as a fraction. So the quotient of a number and 7 would be x divided by 7, or x over 7. So that's that part right there. But what I want is the reciprocal of that, because that's what I'm going to multiply by 6. So the reciprocal of the quotient of a number and 7 would be 7 over x. So my expression is 6 times 7 divided by x. I'm going to put this in parentheses just so it's clear. And this would be nonlinear. And the reason for that is that this could be rewritten as 6 times 7 times 1 over x, and then that 1 over x could be written as x to the negative 1. So x to the negative 1, the power on that term does not qualify for a linear expression, so this one would be nonlinear. All right, let's tackle number 4. Number 4 says twice a number subtracted from 4 times a number added to 15. Okay, so we're going to let x be the number. And so we want twice a number, that would be 2x, subtracted from 4 times a number. Okay, so the 2x is being subtracted from the 4x, and all of that is being added to 15. Okay, so when I do these, I like to reread them. Twice a number, we've got twice a number subtracted from 4 times the number, and all of that is added to 15. Okay, so there's our expression. This one is linear because all the variables are to the first power, and there's none to any other power, and so it's a linear equation. All right, let's look at 5. The square of the sum of 6 and a number. Okay, the square of, so we're going to square something. And whatever I'm going to square, I want to put in that parentheses. So the square of, we're going to square a sum. So we're going to be adding something together. So we're going to square the sum of 6 and a number. Whoops, I forgot to say, let x be the number. Now I know this is getting a little monotonous on some of these to just always be writing let x be the number, the number, the number. But sometimes x, and you saw that in the first lesson, it's not always clear what you're going to define x to be. In some of these, it's just the only variable in the phrase. Okay, so the square of the sum of 6 and a number. Okay, so we've got 6 plus x squared. And so we have to think about what the power on the variable is here. And this would be non-linear. Okay, because even though the square is outside the parentheses, the x is going to end up getting squared. And I can use the distributive property to multiply this out. 6 plus x times 6 plus x. And we're going to end up with an x squared, because this is going to be 6 plus x times 6 plus 6 plus x times x. So you can see that I'm going to end up with an x times x here when I multiply that all out. Don't worry if you're not real good on multiplying expressions like that out. We'll be practicing that. But that is a nonlinear one, and that's why, because there's a power of 2 on the variable. Okay, the next problem says the cube of a positive number divided by the square of the same positive number. So we're going to, we are going to let x be the positive number. Okay. I really do have good handwriting, but it's hard to write with this thing. We're going to let x be the positive number. So, how are we going to translate this? The cube of a positive number. So the cube of a positive number, and our positive number is x. So the cube is the third power, so it'd be x to the third. And that's going to be divided by, so remember we're going to use the fraction bar to do that. Let me rewrite that. Divided by the square of the same positive number. So it'd be x squared. Okay, so this looks like it would be a nonlinear expression because of the powers on the variables, but if you look at how this would simplify, this would be x times x times x divided by x times x. So this simplifies down to x to the first power. Using exponent rules, I would say x to the third divided by x squared is x to the 3 minus 2, or x to the first power. So it would be linear. Okay, our next example here is the sum of 4 consecutive numbers. Okay, so this one, the sum of 4 consecutive numbers, let's let x be the first number in the series. So to write consecutive numbers, I'm just adding 1 each time. So I've got x plus 1, x plus 2, x plus 3. Those are all being added together. So all the x's are to the first power. So it is linear. All right, let's look at the next one. Okay, so check your work here. 4 subtracted from the reciprocal of a number. We're going to let x be the number. So the reciprocal of a number would be 1 over x. And then 4 subtracted from that would be 1 over x minus 4. This expression is nonlinear because 1 over x is the same as x to the negative 1, and that is not a power of 0 or 1. So it's nonlinear. All right, let's look at the next one. All right, so number 9 says half of the product of a number multiplied by itself 3 times. So we're going to let x be our number, and then the number multiplied by itself 3 times would just be x times x times x. Half of that product would be 1/2 times x times x times x. But we could rewrite this as 1/2 x to the 3rd power. So this would be nonlinear because of that, because of the power of 3. Okay, let's move on. Number 10. Okay, so number 10 says the sum that shows how many pages Maria read if she read 45 pages of a book yesterday and 2/3 of the remaining pages today. So there's a couple different ways you could actually do this. I chose to let x be the number of pages in the book, the total number of pages in the book. And so then Maria, the expression that shows how many pages Maria read, would be 45, because she read 45 pages first. And then the remaining pages of the book would be x minus 45. And if I multiply that times 2/3, that would represent 2/3 of the remaining pages today. So she read 45 plus 2/3 times x minus 45. And that expression would be linear because the power on the variable is just the first power. Okay, number 11. An admission fee of $10 plus an additional $2 per game. So how would we represent that? So this is a situation where you have a flat fee, an admission fee of $10 plus an additional $2 per game. So this could be bowling or golf, or I'm not sure what it would be, but it's a situation where you could play multiple games. And so our variable is going to be the number of games that gets played. So we're going to let x be the number of games. Then this phrase here can be represented by 10 plus, I'll even put $10, plus an additional $2 per game. So it would be 2 times the number of games. And that's $2 times the number of games. So that would be our expression, 10 plus 2x. So that would be linear. The power on the variable is 1. Okay, this has been quite a few examples, but seeing examples is helpful for this type of thing. And algebra is like learning a new language, and so you have to see lots of examples of it before it becomes like second nature to you. So this last one here says 5 more than 4 times a number and then twice that sum. So here's what I got for that. 5 more than 4 times a number. So I'm going to look here at 4 times a number. This time let x be the number. So 4 times the number would be 4x. 5 more than that would be 4x plus 5. And then twice that sum. So the sum of 4x plus 5, I want that twice. So I need to put parentheses around it so that the whole thing gets multiplied by 2. So it'd be 2 times 4x plus 5. And that is linear. It could be rewritten as 2 times 4x, which is 8x, plus 2 times 5, which is 10. So that's a linear expression. The power on the variable is just 1. Okay, I just want to point out that on your problem set page, you have this lesson summary that gives you sort of a definition and some examples of linear expressions and nonlinear expressions. When you're doing these problem sets in this module, they're often looking like this without very much room to write. So my recommendation would be not to squeeze it in to these lines. Either go to the bottom of the page, and if there's enough room there, you could write it there, or just put in a piece of binder paper. Yeah, there's no room on this page. So you've got 15 of these to work on for homework. Get a sheet of binder paper and just insert it into your notes and do your work on there. So you're not cramming your work all into one page. Okay, good luck with that. Have a great week.